Yeah, sorry. So I was saying, yeah, diffusions are very important to understand if you're planning on going into the area of generative, into the generative area side. Okay, that being said, I wanted to first discuss a little bit about the basics of diffusion itself before actually going to the numericals. Like I said, it's something which is new compared to all the other things which we have discussed. So let me just first discuss very briefly about the working of diffusion, and then we can go to the numericals. So, like I said, diffusion models are a type of generative models. And what is the aim of a diffusion model? So, if you look at the figure 2, which you see on the slide, the aim is basically given a noise, which is shown in the bottom. We need to generate an image like it is generated on the right side. So, this is the aim of any generative algorithm. It's the same as the objective for a diffusion model. How does diffusion do that? So, there are two steps in diffusion. One is called the forward process, the other is called the reverse process. Remember that this forward and reverse is not the same as the forward pass and reverse pass in deep learning or the neural network training. Those are different. So here diffusion itself has a forward process and a reverse process. What do you do in the forward process? You start with the image, like you see on the right side, which we call it x0 at this point, and then you keep on adding noise to this image and keep on moving into the next time step until you complete to a time step capital T, where you end up with only noise. So you start off with a clean image which you see on the right side, then you keep on adding some Gaussian noise and until you end up with just the noise. This is the called the forward process. Now, what is the reverse process in diffusion? Reverse process is where you start off with your noisy noisy input, like the one which you can see on the leftmost side, and you keep on denoising this noised image until you end up with a clean image on the right side. This is the reverse process. So, how do you look at it, or how do you model this process itself in a more mathematical terms? So we call the forward process is modeled using something called as the q of xt given xt minus 1. This is the distribution. And the reverse process ideally is modeled using p of xt minus 1 given xt, but it is intractable to identify what is p. So people use an approximation with the help of neural networks, and that is where you get this p theta. P theta of xt minus 1 given xt. This is how we model the reverse process. So first let's look at the equation for the forward process first. So I won't go into the entire details. You can look into the lectures. I'll just show you the important equations and then we can go ahead with the problems. So the equation, first important equation is the forward process modeling, which is shown over here. Q of xt given xt minus 1 is equal to a normal distribution given xt for an input xt, and the mean is nothing but root of 1 minus beta xt minus 1. The variance is nothing but bt of I. So it's a multivariate Gaussian, and here the covariance matrix just has elements on the diagonal, and that too it is nothing but beta of t. So this beta t is a hyperparameter. Usually you have schedulers for it. The official paper used linear scheduler. You can use cosine scheduler, quadratic scheduler. We can see a bunch of different things today in the code. You can use any schedulers for beta to keep on reducing it as the time progresses. So this is how you model the forward process in diffusion models. Now let's look at how you model the backward process. Like I said, we can't have a closed form, or we can't get the exact solution for the backward process. So we approximate it with the help of a neural network. That approximation is called p theta of xt minus 1 given xt. That again is modeled using a Gaussian distribution where you have the mean as mu theta and the variance as sigma theta. In the official paper, which DDPM was proposed, people have kept this variance constant. But in the later papers, in certain variations of it, people have also modeled sigma theta. But for today's case, and I think even for the lecture most of the time, sigma is assumed to be a constant, or we don't learn sigma. All we learn is the mean mu theta. And then professor has discussed few techniques called the reparameterization techniques, where you, instead of predicting neural network predicting the mean of the distribution, you just predict what is the loss. uh, I'll just show you this. So this is the algorithm. So you try to predict this second part of the loss function, which is epsilon theta of this entire term, root of alpha bar t x naught plus root of 1 minus alpha bar t epsilon comma t. So this is what your neural network is trying to predict. What is this term? This is the noise that has been added to the noisy image which you're taking as input. The noisy image is this part, root of alpha bar t x naught plus 1 minus root of alpha bar t epsilon. This is the noisy input image you're taking. And your goal of the neural network is to predict what is the noise that has been added to the original image to get this noisy input. And you know how much noise has been added, the ground truth, that is the epsilon which you are getting. So nothing but you're finding out the simple terms, you can say you're finding out the roots mean square error between these two. That's the most simplest way of understanding this loss. So how do you go from how do you justify theoretically that you want to predict mean, but instead of that you can just predict this? That involves a lot of derivation which the professor has gone through, which again uses the same derivation as the VAE encoders, elbow bounds. Then you find the reparameterization trick, and it follows a similar type of derivations. But all you need to know is the neural network tries to predict what is the noise that has been added to your given input image, and what how far it is from the ground truth noise that was actually added to that input image. That is what you're trying to predict. This is the training time. Sampling time we'll discuss when we come to the code part of it. But I hope the basic idea of diffusion models are clear. Is there any doubts or anything that is unclear in this? We can go through it again. Okay, then if this part is clear, then let's move to the numericals itself. Okay, so the first MCQ is very simple. So which of the following represent a valid transition matrix for a Markov process? Like you remember, a transition matrix in Markov process basically talks about what is the probability that when I'm in this state and I'm moving to the next state, what is the probability that is there. So that is why you're having these values. These values indicates the probability of transitioning from your row state to your column state. So identify which are the valid transition matrix out of these four. I'll just pause for a quick second. You can post your answers in the chat.
I think first and A and D.
Okay, okay. C is definitely not right. Answer is actually A and D. That's true. So all you need to do is basically to identify something as a valid transition matrix is basically sum up the rows and it should be equal to 1 because they're all probabilities, right? So from a particular state, let's look at the first example. So there are two states possible. The For the first row, state 1 is the first row first column, state 2 is the first row second column. So there are only two states possible. So obviously the probabilities should sum up to 1 across the rows because you can't go beyond that. Transition, like I said, it determines the probability of going from one state to another state. So in the first one, when you sum the rows, they're equal to 1. The second one, not all the summations are equal to 1. The third one, the summation is not equal to 1 because 0.5 plus 0.3 is 0.8. And the last one also, the summations are equal to 1. So in this way, you can say that wherever the summations of each row equal to 1, it means that that is a valid transition matrix. I hope this is very simple. I hope it's clear. Any doubts in this? Okay, great. Let's move to the second question. So I just explained how you model the forward process in diffusion. Then which of these following are the correct way to model the q of xt given xt minus 1? So it's a direct formulaic question. You can think of it. Just see which of the options actually can be used to model the q of xt given xt minus 1. There are certain conditions based on beta t, if you remember. So you just remember that condition for beta t and you'll get the correct answer. I'll just wait for a second.
A and B.
It's correct. A and B is the correct answer. So, ideally, you can find out the solution by solving the recurrence equation and note the convergence that it is converging to the Gaussian distribution. That is a bit more hard if you go completely solving it. Simpler solution is, let's look at the equation itself and try to deduce what is happening. So the first one, it's both of n is normal distributions. That is clear, I guess. Then let's look at what we want to achieve. We want to converge it to a Gaussian, standard Gaussian. What is a standard Gaussian? Where the mean is 0, deviation is 1. That is what we want to converge. And like I said, we have the square root of beta t xt minus 1 as the mean. And here 1 minus beta t into I. And beta t is a decreasing, linearly decreasing. So what is the, like, convergence is when you're almost reaching to infinity, right? Like a lot of time. So what is the least, what is the last value that beta can get to at convergence is 0. So when I say 0, then immediately this distribution becomes a standard distribution because the mean will become 0 and 1 minus of 0 is 1 and the variance or the standard deviation is 1. So first is the correct option. Now let's apply a similar logic. Even cosine beta t is again following a cosine scheduler which keeps on decreasing. Here also, if you think about it, cosine scheduler, the max value it can go is 1. And here the beta value mean will become 0 over here. Similarly, here 1 at the convergence, beta will become 1. And that is why you get the standard deviation as 1. So this is a simpler way, official or like more mathematical ways to solve this equation, recurrence equation until convergence. So the other two don't follow. You don't get to Gaussian distribution. The other two solutions. You might if there are certain types of transformations existing, but none of them are existing for both Poisson and Dirichlet. So you can't do that. Okay, let's move on to question number 3. So there are 4 statements regarding DDPMs, that is the diffusion models, denoising. Sorry, I forgot the full form. Based on the diffusion models, just select which of the following are the
I think A should be correct.
No, A is not the correct answer. Just think about it more clearly, because there is one term that is very strong in this A, which is not true. Even D is also not true. Just think about the advantages of diffusion models over disadvantages of diffusion models over VAEs and GANs. Yes, C is the correct answer. So let's discuss. I have explanations, but let's discuss once option by option. So why A is wrong is because it says that DDPMs explicitly learn true score functions, but that is not true. DDPMs implicitly learns. There are certain types of diffusion models that came later, which are score-based diffusion models. Those learn more explicit. But DDPMs officially, when they published, there was nothing that was pointing it out to explicitly learn a true scoring function. It learns something similar to what a scoring function does implicitly, you can say, but it's not very explicit. So that is why A is false. And B is very similar to A. Here we are saying in classifier guided diffusion sample, one learns the true scoring function in a supervised manner, which is again true. It doesn't learn the true scoring function at all. That is not the goal over here. The goal over classifier diffusion model is to guide the diffusion to generate the images in a for a specific type of a class with the help of the gradients. Option C, it is true because we can sample images faster than diffusion models like VAEs or GANs. Like we know, diffusion models is a time-taking process because there are like T time steps that has to be completed before you finish your generation. So diffusion models in general are a bit slower compared to other generative models like VAEs and GANs. The last one says classifier based is works better than classifier free. Again, this is not entirely true. Both of them have their advantages and disadvantages, because one has less time complexity, one has better in certain other sense, but there is no explicit way to say that one is better than the other. So option D is also false. Okay. Let's move on to question 4. Again, there are 4 statements regarding diffusion models in generals, and just identify which are the false statements, not the true, but which are the false statements.
D. D answer.
These false, but there are other false statements also. There are multiple false statements. Yeah, A is also true. Maybe let's just discuss the answers. So the correct answers, which are which are the false statements? It's A, C, and D. There is only one true statement which is there in these 4, which is the B. So let's look at each option one by one. So first one says diffusion models can only generate samples directly in the domain of the data itself. Wrong. Diffusion models can generate outside the domain also. That's why it is more universal and versatile. It can generate in today's world. If you see, it can generate a lot of different things, even out of domain, like audios and all. It can generate. So it's very useful. Option B says generic diffusion process can be designed using stochastic differential equations based on Wiener process, which is true. This is can be used based on Wiener process. You can generate SDEs basically. So option B is true. Option C, can everyone mute themselves? Yeah, thank you. So option C says diffusion models sample based on ancestral sampling in the forward process. This is wrong. Firstly, you have to remember that there is no sampling happening at all during the forward process in diffusion. Sampling happens. I wouldn't even say sampling actually. Some There's no sampling per se happening at all in diffusion. In forward process, all you do is you keep on adding noise on it. You're not sampling any model. Ancestral sampling is in fact something that is used in most of these transformers or LLMs in autoregressive way, but diffusion models don't actually use that. So there is no sampling as such happening. So that is why C is false. Option D says that one learns a score network which predicts the mean of each intermediate distribution in the forward distribution process. Again, like I was explaining, we don't predict the mean anymore. We predict the noise from the neural network. That is the goal, right? We stop predicting the mean and we somehow manipulate it using the parameterization technique and all, and predict the noise that we want that is there in that particular noisy input data with the help of the neural network. So correct answers are A, C, and D. Okay, let's go ahead. So this is very small numerical. It just based on the idea of how much you understood on the working of diffusion. So let's say you have a forward diffusion process where the initial point is data point is 3, and the noise variance beta, which is beta t in our case, is fixed to 0.4. How many time steps would it approximately take for the variance of the noisy samples to reach 0.99? Remember, the beta is fixed. We are not reducing the beta anymore. It's fixed for every step, which is 0.4. Identify how many time steps you would need so that the variance is now 0.99. Okay, I'll quickly wait for a minute. You can just try to solve it and let me. Maybe let me discuss it. So the correct answer is 9 time steps. So let's first look at the solution. What are we trying to what do we want? We want how many time steps does it take for the variance to reach 0.99 value? And as you can know, variance is nothing but 1 minus of 1 minus b beta. And since it's constant, you keep on multiplying 1 minus beta, uh, like t number of steps, let's just say. So your variance after time step t is 1 minus 1 minus beta whole to the power t. And we know that beta is nothing but 0.4, which is fixed value. And what are we left with? We are left with 1 minus of 1 minus 0.6 whole to the power t equals to 0.99. That is what we want. We need to identify the value of t, which is nothing but 0.6 whole to the power t equals to 0.01. Just add logs on both the sides, and the value you get is t is equals to 9, approximately 9 time steps. So this is what, it's a very simple thing. All you have to understand is every time step the variance keep on multiplying with itself, and this is what the equation you get, and then it's just substituting the values. Okay, I hope this is clear. I'll just move ahead. If you have any questions, do let me know.
Yeah, regarding the previous question,
Yeah,
at what step of the diffusion it happens? It is
ninth
calculated
step. Ninth step, right? T is equals to 9.
9 steps. It is for calculating the number of steps in the forward process.
Yes.
Okay.
So in every forward process, if you, as I explained previously, in every forward process you keep on adding some noise, and the equation which you remember, right? Q is equals to normal distribution of uh, beta of mu. Wait, I'll just show you the equation. This is the equation, right?
Yeah. Okay. And objective is to get the
Variance to
Gaussian distribution at the
exact,
step.
exact.
Okay. That's why we calculate variance of that, and how the and what is the relationship of variance with respect to noise?
No, we
Acha, at
yeah,
every step the variance will change.
yeah, variance depends on the noise, right? Because variance is nothing but beta.
Okay,
That's what we model.
okay. Noted.
Yeah. Okay. Let's move to question number 6. When training diffusion models, does the learning remain invariant of the weights of the reverse process time steps? It's a simple yes or no question. Just think about it. It's saying whether the weights during the training of the neural network in the reverse process is invariant to the time steps or not.
weights will change in the reverse process,
No,
right?
no, changing is different, but will it get affected in the across the time steps? Weights will obviously change because you keep on updating, but will they affect across the time steps or not? Does the time steps play a role during the weights or not?
Yes, there will be impact because variance and everything will change, right?
So yes, that's true. It is invariant. So the correct answer is it basically changes. It's not invariant. So the correct answer is no, it's not invariant. So like you explained, it is the reverse process is conditioned on time steps. So you need to have an idea at what time step you're working on, because based on the time step, the weights are also adjusted accordingly to predict the noise. So weights are not invariant to the reverse process time steps. So yeah, these are the six numerical questions. Any doubts on this? If there are no questions, we can move to the code. Okay, then let's go to the code part of it. So this was the same. I was discussing about what the diffusion models needs to be done, like a basic working of them. You can read through it in more thorough. The code will anyways be given. You can look at it later. Let me just. Let me start from the start. Yeah, so I think by now this is the official paper that was published in 2020. DDPMs, denoising diffusion probabilistic models, which again is not a very. It's not. This is not the paper that proposes diffusion. Actually, it was a paper in 2015 that actually proposes the idea of diffusion. These people just refine it better and make it applicable with the help of neural networks and all. And then in today's time, people from Google, OpenAI, Meta, they've used diffusions in a very large scale level, and that's why it's very famous. So let's look at how you can implement a simple DDPM. So there are a lot of new concepts over here. I wouldn't say new concepts; it's kind of the old concepts only, like the attention convolution and all. But the way it has been written by the authors, so here we use a bit of new libraries. Especially, there are two new libraries which we use. The first library is called the this library called EIN OPS. So the full form of this is Einstein operations. So this is a library that you can download. So what is the benefit of these Einstein operations? It helps you perform the same tasks that you perform in PyTorch, like rearrange or masking, or like reducing the shape of a tensor, or reshaping whatever things you do. You can do that in a much more simpler way using Einstein operations library. I'll show you how it is done. Then there is also Einstein summations, which is again we can perform all these PyTorch operations like matrix multiplication, dot product, summation, etc. All of them in a very simple string way. We'll come to it when we're doing so. So these are the two new things which you see today: Einstein operations library and Einstein summations function, which is present in PyTorch. Apart from that, everything else is already existing. Oh yeah, one other library called as partial, which is coming from func functional tools, basically func tools. What does partial do? So basically, if you have a class or a function that has certain arguments and you want to fix certain arguments to a particular value which should not change throughout the execution, you use partial. So partial, when you call the partial, you mention what is that class or function, what are the arguments that has to be fixed, and then that will be fixed throughout the execution. We'll see how we will use partial in the code. So I think yeah, these are the new things that is different from the previous codes. So okay, like one thing you have to remember is this is again a generative algorithm, right? So you need something like an auto encoder, and the official authors used UNet. They use slight variations in UNet, like in original UNet they use ResNet and all, but the authors use ConvNext to make it better. They also added a bit of attention in between, and they also add positional embeddings. So the core of the architecture which is used to generate or denoise the image in the reverse process is a UNet architecture. And as you remember, UNet architecture, It was famous because there were some residual connections between the encoder from the left side to the decoder, and because of this, more semantics were learned properly and thoroughly. And the goal of a unit architecture is take something as an input, let's say an image like 3 cross 64 cross 64. It downsamples first into a bottleneck layer, then it upsamples using the decoder, and the output will be of the same dimensions. And there is some residual connection between the encoders and the decoder blocks. Now, let's first look at some helper functions which we will use in the creation of the network itself. The important ones are these three. First is the residual class, which you can see. Next is the upsample and downsample function. Residual class, let's see what it is trying even to do. It is basically creating the residual connection. You take the input, then you push through like a forward pass through one layer, and then you add the original input to the output of this forward pass. That's what you're doing in this line. Self fn is a function or a layer that's like a, you send x through that particular layer, get the output, add it to the input. This is what a simple residual connection is. So that is what we're implementing over here. We'll use this throughout, so that's why we created a separate class. Next, we have two simple functions, upsample, downsample. So upsample basically uses convolution transpose. So convolution transpose is a, I think we've studied during the start when we were talking about convolutions. There are two different types of convolutions. One where you downsample or you reduce the size, that is your normal conv 2D. Then one where you go from a smaller spatial dimension to a higher spatial dimension, that is using the convolution transpose. So that's what upsample function does. It just simply uses a convolution transpose. Arguments remain the same. Whatever is the input channels, output channels, kernel size, stride, and padding. So these are the two different functions which are like a helper functions which we'll use later. Okay, next comes position encoding. So in attention and all, when we discussed transformers and all, but position embedding was very clear, right? Like what were we using position embedding over there for? Let's say your input has like a text, today's cold. So you know that every word comes at some position in the entire sentence. So that is why you use positional embedding, so that the model knows that when you're processing that particular word, you need to keep in mind at what position that word is in the entire sentence. But I would ask you a question. Where do you think we will use position embeddings for diffusion models? Like at what stage in the entire diffusion execution do we use position embeddings? Any guesses? Okay, let me explain. So here we use during obviously in the reverse process when we are denoising the image. But why do we have to use? Because if you remember denoising, let's just look at the diagram. So in denoising, you start off from the complete noise. You keep on removing the noise in every time step, a little by little. So let's random. If you remember the training of it, you randomly pick a particular step, right, at xt. That's what the entire reparameterization and technique and all that helped us make it simple. Is that you can start off from any position, and since you have a equation that is dependent on the original image, you can just identify what is the noise that has been added to the original image, and you try to predict that noise that has been added to the original image. But when you pick at something time step t, the weights in the previous last question which we discussed, they are dependent on that particular time step t. That is what information you need to give to the model. Okay, this particular step which you are incorporating, it is somewhere in between this entire from capital T to 0. At what position it is, that if it has an idea, then it will correctly predict what type of a noise that has been added. So this is where your positional embedding comes into picture, because you need to give some sequential idea or the time frame to the model which is predicting the noise, because noise depends on the time step at which it is present in the entire unraveling of this denoising process. I hope this is clear. Any question in why or where we are applying position embeddings? Okay, where I'll show you, but I hope you understand the motivation of it.
Yeah, I understood about positional encoding, but that is sinusoidal. So, what is the difference in normal position in embeddings and sinusoidal.
Also, it's just the same thing. Like positional embeddings can be used whatever you want. It could be sinusoidal, cosine, or like even when we discuss in transformers, there are a bunch of different positional embeddings. You can use anything. These paper official people use sinusoidal because that's a more standard embeddings that was used in transformers paper, right? So that is why they used. You can use any type of embedding, positional embedding.
Okay, though did not specify what embeddings.
No, they specified sinusoidal.
Is there? Okay.
Yeah, in the official paper, they mentioned that they use sinusoidal position. And it's the same equation which was used in the tension is all you need paper. This is, if you remember, this was the equation. Oh, wait. Here we wrote it in a slightly different way. We had the equations written to us directly in sine and cos, but here we are first calculating the embeddings and then we are doing dot sine and dot cos. But the equation remains the same which we used in the transformers itself. It's just a little bit interchanged over here. We are doing sine and cos later, but over there we did the sine and cos and we divided to them. Remember sine and cos because even positions needed sine, cos for odd positions.
Okay.
Yeah. Then let's look at the blocks. Like I said, originally DDPM authors employed wide resonate block. I think Swati, can you unmute because there's a noise. If you have a question, you can. Yeah, thank you. So originally DDPM authors actually used wide resonate block, but there is a person Phil Wang. He decided to also have a support for convex blocks, and they showed it is doing a bit better because convex is obviously better than resonate. We'll show the implementation for both. The code anyways is we've written for resonate previously and convex also, so you can just look at it. Okay, before that, let's first look at what is the block class needed for. So this block class, you can think of it like you can think of it as consisting three important things. One is your convolution layer. Next is your group normalization. Then is next after that is your activation CLU function. Okay. Any idea or guesses? Is what is group normalization? Anyone? I think professor has covered it, but still, any idea or guesses what group normalization is? I'll give you a hint. It is kind of a hybrid between your batch normalization and layer normalization. Okay, let me explain. So in batch normalization, what do? You normalize across batches. But the problem is when your batches are very small and you really can't normalize because what is normalizing? You're identifying mean and deviation, right? Now, when you have less samples, your mean and variation, standard deviation which you're approximating is not correct because the higher the number of samples, the mean and standard deviation that will be approximated is more and more closer to the actual mean and deviation. So that's why batch normalization fails when you have smaller batch sizes. Layer normalization finds out across a particular layer, across different spatial and channels, what is the normalized value. Over there, the problem is the spatial information is kind of getting lost during the normalization. So to overcome these two, group normalization says, let's say you have n number of channels. Divide the n number of channels into 6 groups or like g number of groups, and each group you normalize separately. So here we are overcoming the problem of batch and layer normalization. So that is what group normalization is advantageous. So you can definitely try out for other tasks also where you're using batch normalizations, or if you have some, you can just try out group normalization and check how the accuracy changes or is there any improvement at all. So the idea is here that you divide a number of channels.
Sorry to interrupt. This group normalization, it will be called for each layer, is it?
Yeah, here whenever you're calling block, you call block actually. A block consists of three things. First is your convolution, group norm, and CLU. So if you look at the forward function, what are we doing? We first send the input to the convolution layer, take that, send it to the group normalization, then take that and send it to the activation.
In the forward process.
In the forward process. So whenever you call a block, a group norm is called after the convolution. But whenever you're calling convolution separately apart from the block, it's not necessary that group norm needs to be called. It depends on where you want to add the group normalization. It's just like a normalization of batch normalization, right? You can add anywhere you want batch normalization. It's not necessary that it should come after every convolution. Sometimes you don't have to do it.
Okay, and how the noise is added? Because in forward process at every step,
Oh no, this is not that forward process. So in the start, I said neural network and diffusion, the names are using the same. Diffusion, we say forward process and reverse process, but that has nothing to do with the neural network's forward pass and backward pass, which we've been seeing till now. These are two different things. Here also, firstly, we are not talking about forward pass at all. This is just a class, neural network class. If you remember, we talk about creating a class, then have two important functions: init function and forward function. This is just that function. There's nothing about neural networks forward pass till now or anything.
no, what I want to understand, entire diffusion process,
No, no, there. That's what I'm saying.
where it fits.
Just I'll explain it. Like, we are starting with the element block over here. We build ResNet blocks on top of these blocks. ResNet blocks we use to create the unit architecture. That unit architecture will come into the reverse process.
Okay, so the entire things which are explained here, group normalization, that will come in unit, which is
Yes,
backward backward process in diffusion.
exactly, exactly.
Okay, got it.
But during the backward also there will be a forward pass and backward pass for the neural network. Remember that. That is different.
Okay, okay,
Okay, it's easy to confuse. That's why make sure you have this distinction.
okay, sure.
Yeah. So this is what a simple block looks like, where you have just these three elements. I'm not going in depth about what are these init and forward functions, because by now I am assuming all of you are familiar with it. It's the standard neural network classes which I have been creating till now. Then we'll create something called as a ResNet block class. Here, what do we have? We first create an MLP layer, which consists of a CLU activation and linear layer. This gets activated whenever you're sending the time. So time embeddings also needs to be processed and attached to the model, right? To the embeddings of the images. When you're processing the images, time also gets processed separately, and both of them gets added, and it goes to the next layer. So that is what the time embedding is processed using a simple linear layer. Then here we call the previous blocks which we defined, we call two different blocks, and we again create a simple convolution of conv2d, which we call resconv. So these are the elements that are present in ResNet block. Now let's look at how the data flows in this particular ResNet block. You get your input, you send it to block 1, then whatever output you get, you add it to the particular time embedding. If so, here if it's a small if condition, if you have a time embedding which we will send as an input. So you first send the time embedding to the MLP for processing, then you add the time embedding to your previously processed images H. So that time embedding is added to H, and that particular H is then sent to block 2. Then that block 2 output is again sent to another convolution, which is added in a residual way to the original input, and that is what is written. So let's look at one small thing over here, rearrange. So like I said, this is a term which has been coming from a new library called functools. So you can see it's very simply rearranging the tensor itself. You can just mention in form of a string and it will automatically rearrange. So previously you had to write that dot reshape or unsqueeze 00, some other PyTorch operations. But here it is very simple. Just call rearrange, mention the tensor, mention what you want it to rearrange. You want to go from dimensions BC, which is existing dimension of time embedding, to BC11. So now we are expanding into 4 dimensions. That's it. It's a very simple way. You don't have to worry about more having the operations reshape or unsqueeze and all those things. So this is the benefit of having this rearrange. Similarly, the same benefit is there when you use that Einstein operations and Einstein summations. We'll see that later. So this is a ResNet block. So we get the input, then you send it to the block 1, add to the time embedding, send it to block 2, and then append it to the ResNet convolution of the original input. So this is your simple ResNet block. Let's go to the convex block. Again, we follow what the convex has proposed, their novelty. Here we do a similar type of, first we do a group normalization, conv2d, GLU activation layer, group normalization, and another conv2d. And then we also have an MLP to process the time. Here we have the DS conv, which is the similar simple convolution layer, and we also have a ResNet conv. how do we see at the forward pass? We first send it to conf dsconf. We then uh, process the time embedding if that exists. Then you add that to the output of the previous dsconf. Then you send this to the entire network, sequential layer network, which is these four layers which we defined on the top. Then that output is again added in a residual connection way to the input which has been processed to a convolution layer. So don't worry about where this exact architecture, that you look into this paper, which is nothing but the convnext. But I hope you're clear with how you're processing the data. The structure of the data is clear, which is the same as any other CNN network. But in case if there is anything unclear, just let me know. I'll just quickly pause for a second.
No, instead of transformer architecture, this convenext is used, right? Those are two alternative options.
No. Transformers and convenext are not alternative options, not necessary. Convenext is just inspired from how the transformers used to work, and then they created something built on only the convolution layers. It's not an alternative.
So they could have used transformer block itself rather this.
We have, in this particular, I'll show you, we are using next transformers. You have next attention module if you see it in the below.
Okay. Once they use this convenext, then they are using a attention model. Okay.
Exactly.
Convenext
Convenext was proposed because they saw that there is an advantage in how VIT models were performing, or transformers were looking at and processing the features. But the problem with them was those high computations, right? So they wanted to still stay with convolutions, but at the same time get the benefits of what VIT was processing.
Okay.
Yeah. So you can use in conjunction, because attention, see, whenever I say attention, it doesn't have to be a transformer. Transformer is nothing but multiple attentions together, those encoders and decoders layers. Attention itself can be used anywhere. If you remember in image captioning models, even before these attention as transformer models came, attention was used in BERT and all, right? So attention is nothing but a simple operation that can be used with convolution layers also for image captioning tasks and all. It doesn't have to necessarily mean that attention will only be used with transformers.
Okay.
Yeah. So here we use attention. We have two attentions. That's what I'm discussing next. We have multi-rate attention and linear attention. So linear attention is a variant of multi-rate attention. So if you remember multi-rate attention, we used to do the dot product between Q and K. So that had a quadratic complexity. Linear attention, we don't do that. We overcome that and maintain a linear complexity. I'll just show you how to do that. But yeah, we have two attention modules, linear attention and multi-rate attention, that we will use after the convenext, on top of the convenext features. So let's look at first the multi-rate attention. We create the class attention, and then we, as usual, this is the same neural network class. So we make sure that we import the nn.module. Here we define a bunch of different variables, number of heads we want, what are the dimensions of the head, and then these are the two things which we are creating. We get the output from the convolutions, right? Then we have another convolution where the number of channels are multiplied by 3. So existing number of channels we multiply by 3. Why? Because each of the number of input channels which you are getting, that will be corresponding to one Q. The second one will be corresponding to K. Another one will be corresponding to V. Not directly. We need to do some more processing. I'll show you how. But yeah, so the convolution layer will take the input number of channels and then multiply it to 3 times of the hidden dimension, head dimension, which we want. Why 3 times? Each channel, each dimension channel will correspond to one of the QKV values. That's why 3 times. Then we have another one. After you finish all the attention, your output is basically nothing but again another convolution layer projecting from your head dimension channels to your actual input dimension channels which you got. So that is what these two convolution layers correspond to. Now let's look at how the data itself flows. So you first get your input X, which is the output from the previous convolution layers. You take that X and then you identify important values like batch size, channels, height and width. Now this particular X is sent into the conv2D, the first conv2D, where you're multiplying the number of input channels through 3 times. And then you chunk that into 3 parts. This dot chunk is basically split the channels in 3 parts. So that is what you get. QKV is now a tuple of three different values, each value corresponding to Q, K, and V. Before going to that, there's a small rearrangement that you have to do. That is what we're using. Again, since we're using a simple rearrange function from functools, you can mention it in string terms. You don't have to worry about it. So what we are saying is currently the dimensions, which you can see, it is in this form: b of h into c multiplied together as one dimension, and x and y, the spatial dimension. We want to transform this into b into h and c. H is the dimension of the each head, and c is number of channels, and you spatial dimension which was there previously x and y, you make it into one big tensor. That's why you're multiplying x and y. You're keeping that into parenthesis. So what we're doing is we are basically saying that the current channels that you have for q, k, and v, those total channels are actually two parts: number of head, each head, number of heads that you have, and for each head what is the channel that you have to have. So we are splitting that b into h into c xy to b h c multiplied with x into y. So this is a simple rearrangement that is happening. So let me quickly pause. Is this rearrangement clear? Because then everything else is standard softmax, sorry, self attention. Any doubts in this rearrangement?
Why this rearrangement is required here?
Yeah, so here when you are after the convolution, we have increased the number of dimensions, and that dimensions will contain both the heads and channels. So for each head, there'll be some number of channels. So there'll be this h and c multiplied. Let's say I have two heads and channels are 6. So this will be 12 actually, the output of the convolution. But the 12 inherently has separate heads and channels because we need to do softmax for each head separately, right? So we need to split that part. That's why this 12 we are splitting it into 6 and 2, 2 and 6. Sorry. Is that clear?
Yeah.
Yeah. Okay. Then you do that for all your QKV vectors, maps basically, and you scale your Q with self.scale. That is a parameter which you define on the top. It's the head dimensions to the power of 0.5. And then here we define the soft max. First we define the dot product. So if you look at it, the product between q and k, previously we used to do qk transpose, right? Q dot k transpose. Instead of that, you can use these Einstein summations. You can just mention, okay, I have my q. What is the dimension of my q? bh What is the dimension of my k? bh What should be my output? bhij. It means that I'm multiplying for this di and dj basically. So that is what the simple, that's what we used to do in the previous also, when you used to do the dot product of qk transpose. But here we're just using a simple string based mechanism. So this is the advantage of using these Einstein summations. It takes time to understand this. If you don't want to do this, you can always go back to using your older ways of writing it manually. That will also work. Okay, and then you you identify the softmax. You also then do the multiplication of this attention with the value vector v. We use the same Einstein summation here. We mention the dimensions and you mention what dimension should be the output. Then after you get the output attention values, after you multiply the attention with the value vector, the out is then rearranged. So what do we have right now? Values bh xy multiplied and d. Now we rearrange into the original thing which we wanted, b into number of heads multiplied with the dimension of each head into one particular dimension, and x and y. Now this is sent to the convolution neural network which we define on the top, this one, to reduce the number of channels to the input number of channels that was coming into this attention block. And that's what you're returning. Okay. Any doubts? I know it's a lot of data flow. It will take some time to understand. Just sit through it. I would suggest sit through it, go through line by line. Everything is very well explained in the text. If you're not understanding that, you take the help of ChatGPT also, or you can also ask me next week. But it is definitely a lot of patience is needed to understand diffusion in the first go. There are a lot of components that come into play. Okay, then linear attention, the flow remains the same. We have these two values and everything. Only thing that differs is how you do the attention mechanism, but the rearranging and all those remains, the ideas remains the same of how you create QKV vectors and everything. The only difference is previously you used to do dot product of q and k, but now you first identify the softmax of q and softmax of k. Doesn't have to be softmax. You can do any projection, but for simplicity, these people use softmax. Then you scale your q vector, and now you multiply k and v. Previously, we did dot product, did a softmax, then multiply that attention value with v, right? But here, the dot product is removed, that complexity is removed. You just directly multiply that softmax version of k with the value vector v, and then you multiply this output context with the q vector, and then you rearrange the output and you return it. So this is how you're reducing the complexity of this dot product quadratic complexity to a linear complexity. So this is a variant of attention mechanism, which is called as linear attention. So here we define another group norm. We use group norm in another way called as pre-normalization. One group norm we use in the bottleneck, but here if you want to use separately with the layers, because sometimes what if you remember the in transformers, right? After attention, we had some layer normalizations happening. So instead of layer normalizations, people use again here group normalizations with the help of this class which we created, pre-norm. So it's nothing fancy. It is just calling the group normalization itself, but we just create another class to have more abstraction. So this will be used either you can use it after an entire convolution block or after the attention blocks. Okay. Now let's go to actually how the unit is created. So this is a simple step by step. As you can look over here, we have first a convolution layer. Next, we downsample, like I said, in the unit blocks. The downsample, what does the downsample consists of? Two resonate or convex blocks. We can use either of them. Followed by group normalization, followed by attention, followed by residual connection, and the downsample operation. Then in the middle network, which is that bottleneck part, we again have a resonate or convex block. After that, which we apply the attention. Now, in after that, we have to upsample it, the decoder part. What are the upsampling layers? Blocks, two resonate or convex blocks, group norm, attention, residual connection, upsample operation. And then finally, another residual or convex block is applied, followed by a convolution layer to get the final output. So this is what a typical unit architecture consists of. And this is what we'll create in the class also. We are just utilizing all the previous classes which we created till now, the convex block, the attention blocks, the resonant blocks, all of them which we're utilizing, and to create the entire unit block, it's a unit architecture. So if you see over here, you first create certain variables like how many channels are there, what is the initial dimensions you want. These are all global variables you define. Here we use partial, here we use partial because we want to fix the arguments for these classes, convex block or the resonate, whatever you're using. We want certain values to be fixed. We don't want it to change at all. So that's why we use partial. So this is one way of using it. You don't have to write this. You can get around with this by making sure you always call that particular argument with a certain value. But it is easy if you fix this throughout. It's just another functionality. Then you remember we created the time embeddings. So here we are saying, putting a if condition, if you want time embeddings, whenever it is true, we are creating a small MLP, the same sequential MLP. If the time embedding is false, you just create none. We don't use anything. In this MLP itself, we are creating the sinusoidal positional embeddings. So here we get the sinusoidal equations which you get. Sorry, we use the sinusoidal equations to get the position embeddings for the input. Okay, then we create two different types of layers, downs and ups, which is corresponding to downsampling layers and upsampling layers. Okay, in downsampling, what do we append? Like I said, we append two blocks of either convex or residual. That's what the first two are. Then you do another, you do first a attention, followed by group normalization, then a residual connection, then you downsample. This is what your downsample layers contain. Your middle layers, what do they contain? They contain your block, convex or resonant. Then you do your attention, followed by group normalization and the residual connections. And then you do another convolution block, either convex or residual. Remember, all of them you're sending the time embeddings. If you do notice that part. Like I said, there are a lot of functionalities. Do notice at your own time also, but we're always sending the time embeddings to these. In the upsampling layers, we have two blocks of the same connext or resnet. Then you do attention, and then group normalization, residual connection, then the upsampling operation. Finally, in the output, after you get from the upsampling, you do one final uh, group convolution followed by a convolution, and that is what your final output will be. So these are all what we created. We'll just utilize the same way uh, in the forward function where the data flows. You start off with your input x and the time which you get. You mention what time you're taking, right? If you remember the training process, you need to mention at what time step your model needs to identify the noise at. So these are the two inputs, x and time. X go to the initial convolutions, you get the output. Time goes to the MLP because here time embedding exists. You get that sinusoidal embeddings attached, and now it's a vector. That is what you're getting as the output T. Next, you start downsampling. You send xt all the times through all the downsampling blocks. Okay, and here you finally get the output, which at every output of every block is saved in this empty list H. Then you go through the bottleneck layer, which was those three layers. Then you go through the upsampling layers, which basically upsamples your entire value, and you finally do your last convolution and you return the value. This is what your entire UNet architecture is, and this is what your uh, reverse denoising process also contains of. So in this way, you finish one forward pass of the neural network that will predict the noise that was there in that time step T of that reverse denoising process. So is this clear? I'll just pause for a quick minute. Any doubts? Anything that is unclear? Okay, great. Let's move ahead. Now let's look at how do we add the noises, and let's look at some images. Okay, like I said, there are different beta schedulers that are possible. Cosine beta scheduler, linear beta scheduler, quadratic, sigmoid. All of them follow certain functions. I think linear, quadratic, sigmoid, it's very standard. It's just following a linear function, linspace, or quadratic is basically you multiply the start values with square root of the functions. That will be the again quadratic base. Sigmoid is basically applying a sigmoid on these beta values which you get from the linear. So these are standard. Cosine follows some equation which is again proposed in an entire paper. Please look into that, but don't worry for now. It's just a simple equation like we use sinusoidal equation, right? Something like that. It's not sinusoidal, it's cosine based now. But look into this paper for more understanding of what exactly it is. For now, you just have to understand that there is some scheduler for beta. You can use any of these four schedulers. In this case, I think we are using cosine schedulers. You can also use linear or quadratic or anything else. Sorry, we're using linear schedulers for this. You can use cosine also to make it better. Okay, now let's look at how to first add or get these alpha values and beta values, right? If you remember. So first we define how many time steps we want, 200 time steps. Define the scheduler you want, linear scheduler. Here we then start defining what should be the alphas. So there are two alphas if you remember. We need the square root of alphas and square root of 1 minus alphas. That's what these two what we're defining over here. Square root of alphas is defined, which is torch of square root of alphas cumulative product. Then square root of 1 minus alpha is nothing but 1 minus alpha's cumulative product whole square root. So what is cumulative product of alphas? We just find out the torch dot cumulative product of all the alphas, which is nothing but 1 minus betas. So betas we are getting from the linear beta scheduler. So I hope you understood. It's a standard formula which professor also discussed. Alphas is nothing but 1 minus betas. That's what we did over here. Cumulative product is just call this function cumulative product of alphas. Then you find out the square root of these alphas, which is nothing but square root of 1 by alphas. I'll tell you where this both are used. But for now, square root of 1 minus alphas is nothing but 1 minus of alpha's cumulative product. Square root of alpha's cumulative product is square root of alpha's cumulative product. Okay, I'm just saying a lot of words, but I hope you get the point. If you're not, I'll just pause. Please let me know if it's unclear. Okay, I think this is clear then.
Initialize with 200 times step.
No, it's not initialized. It's up to 200 time steps will go. You can keep anything. Yeah.
Initialize with 0. This starting.
Yeah, starting with 0. Yeah, starting with 0. If you look at the scheduler, You not zero exactly, you start off with these values. 0.001 ends at 0.002. How many number of time steps you want is 200 in between these ranges of beta.
Okay.
These
values, cosine or linear.
Exactly. So if you look at the linear beta scheduler, beta values starts off with 0.0001 and ends at 0.02, and you want 200 in between values between these range. That is what the time steps define in a linear fashion, like a linearly spaced fashion. That's why it's a linear beta scheduler.
Okay.
You can mention 500 also. That just increases the number of steps in your process.
Yeah, but to get the better results, we have to finalize that value, is it?
Yes, there is always a trade-off because more these types, the more time it takes. So you'll have to find a better hyperparameter for that.
Yeah, just like in normal neural networks, we have that option, right, where we can see in the graphs where the loss is decreasing and
Yes.
points. We don't have such similar option here, like we can see at what time step.
So here you can use that k-fold validation, right? K-fold cross validation is just like imagine it to be number of layers in your architecture, neural network architecture. So for one layer you get one value, for another layer you get another validation value. You pick which one is doing best on the validation. But again, in this case, we have to also take care of the computational complexity. I don't want 500,000 to give very good validation accuracy, but it's taking like 1 hour instead of the other one, which is slightly less accuracy, but it's just doing it in 10 minutes.
Okay.
Yeah. So there is the
We cannot see that through some graph or some exponential graph.
no, you can. That's what I'm saying. You can plot the graphs with these values. K-fold validation plots the graphs, right? When you're doing K-fold cross validation. You can plot, but you have to manually plot it. Like over there also you manually plot it, right? Even when you're doing for loss functions and all, you're keeping track in that empty list. When I always say, you just plot that. In a similar way, you can keep track by writing another for loop on top of it with different time step values.
Okay, got it.
Yeah. Okay. Then you calculate your posterior variance also, which is this values of beta into 1 minus of alpha t divided by 1 minus of alpha t minus 1 divided by 1 minus of alpha t. So this value what you're getting posterior for this particular q of x of t minus 1 given x of t comma x of 0. This is the conditioning on the input image x, and you want this reverse process. Okay. Then here extract is nothing but it is basically helping you to get the value of the time embedding or time step, but in a form of a vector. So that is what this extract function does. So time is usually a number which you send, then you need to output in terms of a batch size and a big vector that needs to be attached to every sample in that input batch size. So that is what this extract function does. And this is, let's say if this is my original input image, it's just a simple two cats image. And you obviously, what do? Usually you do some transformations, right? Like what are the transformations you do? Resize, center crop, to tensor, and here's some extra other transformation we're doing to make it lie between -1 to 1 the pixel values. But here when you're applying the noise needs to be applied on the tensor, but you want to visualize it, so you need to again take that noised image and do a reverse transform to visualize what is that noise image. So previously we didn't have to do that because we never visualized after any of the augmentations or the transformations. But now we want to visualize because we are adding the noise on top of it. That is where this reverse transform comes. It's again nothing but you just start off from the previous last steps what you did. Like you do this ranging from -1 to 1. You reverse range it. You also reverse permute it because in officially the images has height width channel, but like I said, PyTorch the channel should come in the first dimension, so you're just permuting that again. Then you multiply to 255 to scale the pixel values to the original range. Then you convert to the original image format, which is the uint8. Like I always say, images are stored in uint8. You convert it into tensor, right? That's why you convert back to uint8, and then you convert into a PIL image, pillow image, and this is what the reverse transform is. Here we didn't add any noise right now. We will add the noise, but this is what you're getting. Previous image was this. You're reversing. You did some augmentations and everything, and then you're again doing the reverse. You get the original image. In between is where you add the noise and you can visualize it. That will show. Okay. Before that, we need to create two functions called as first is Q sample. So what is this Q sample doing? It first samples a noise from this random distribution, normal random distribution, and then this noise is then added using that equation which we added, root of alphas into q x0 plus root of 1 minus alphas into noise. This is the equation. So this is how we are adding the noise to a particular image at time steps t with the help of the original image. This is just that equation which you're writing over here. Alphas you're getting with the extract. Like I said, you have t is one time step. You get the alphas by making it into entire batch size length, and then you get your alpha values and 1 minus alpha values. Then you multiply alpha values with your x start, 1 minus alpha values with your noise which has been sampled from a normal distribution on top, and this is the noise which you're getting sampled. This is for one q sample. Now that's what, if you want to create the look and the noisy image, you take that noisy image which you created from q sample function which you just created on the top. Take that noisy image, apply the reverse transform to now convert this noisy image tensor back to a pillow image, and you plot it. So this is what your image looks like. So you have a time step t. T is equals to 40 time step. I want to add the noise. I want to visualize at t is equal to 40 time step. What will my noisy image look like? And this is what it's look like. Initially, we had the zero image like this, which is clear. At time step 40, this is what you added the noise. Okay. Now, if you want to visualize it, it's just multiply, like doing a for loop. So 0 is here, 50 at time step, 100 time step, 150, last 200 time step. As you can see, last time step is just completely zero. Completely noise. And here from this last time step is where you start denoising in your backward thing. Okay, now let's come to the loss. Surprisingly, with all the derivations which we had, right, the loss has actually, all the theoretical derivations which you do during the simplification of the objective of diffusion, the loss is very simple for diffusion, at least for the DDPM's part of it. All you have to do is you have a predicted noise, you have your standard noise, ground truth noise, which is nothing but sampling, and you need to just find the difference between them. Like you find the difference between any two regression values, right, during regression. Like you can use an L1 loss or L2 loss or a Huber loss. Huber loss is nothing but a smooth L1 loss. It's just simple. You don't have to worry about complicated loss functions thanks to all the simplifications which you did. So the loss over here is again the same thing. You take any noise which has been sampled, ground truth, that you send into the Q sample to get the noisy image. This is the X noisy, is that noisy image that you now send to the denoise model. This denoise model is your unit which you created from the top. That denoise model takes your noisy image, the time step at which that you have been adding the noise at. Then you predict what is the noise that has been added to this original image to get this noisy image. Now that you have the predicted noise, you have the original noise. All you have to do is calculate either L1 loss of noise and predicted noise, L2 or Huber loss. So I think that is pretty straightforward. I'll just quickly move ahead. In this particular, I think DDPM's official paper uses Huber loss only. So you can follow that. You can use any type of other losses also. Okay, now let's actually do it on the data sets, real world data sets like CIFAR10 and FashionMNIST. As usual, you load the data sets from PyTorch, existing data sets. FashionMNIST is available. Your batch size is 28, image size is 20, batch size is 128, image size is 28, and it's a black and white image, FashionMNIST. So the number of channels is 1. You mention all the transformations you have to do. These are 3 transformations that you're doing. You create your data sets first, then you create your data loaders. Again, I'm not going in detail because it's the same process which you use for any neural network till now. And then after that, you print a particular batch and look. You can just do print batch keys to look at what are the batch keys that are available. Only pixel values are there. Now to do the sampling, this is the algorithm for sampling itself. How do you sample? You start off from, you first sample xt from a normal distribution. Then you start from t is equals to this time step capital T to 1. You have a small noise z, and all you have to do is subtract xt minus this values. Z theta is your output predictions from the neural network, and z theta of xt of t, you subtract the original image with this predicted noise plus sigma t of z. You're scaling the values. So this is a standard algorithm. This equation comes from the derivation of sampling itself that you can look into the lecture videos. But in the code, all you have to do is write a simple for loop and subtract the original image with this predicted noise and the scale weighting values. Now let's look at that. How do we do that? Okay, we first define p sample and then we define p sample loop. P sample loop is basically you run for all the time steps. P sample is when for its one time step. Okay, first you extract your beta t's, then you get based on your beta t's, you get your alpha values, 1 minus alpha values and the alpha values. Then you get the model mean, which is your mu theta, right? That you get based on the output of the model, which is nothing but x minus beta t into the model divided by 1 minus of alpha t, all multiplied with alpha t. So this is the standard equation which we use. It's mentioned equation level in the paper. Okay, and after that, I think, yeah, this is the model mean which you're returning. Return model mean plus the noise multiplied with your posterior variance. Now this is what the sample loop. You do this for all the time steps starting from capital T to 0. That's why you're using reverse time step. You keep on calling the p sample and you add the images to the sample. Let's look at how it okay, now the training part. So okay, let me go with the training part, then I'll show you the output of the sample images. So training part is usually just create an instance of your model. First identify what device you use, create the instance of the model, create the optimizer, and you have the same two for loop, epoch for loop and batch for loop. Here it's simple. You take the original image, you create a time for time step over here, how many time steps you want to create based on that, and then you have the losses, p losses calculates that forward pass and that even calculates the loss, Huber loss. You mention which type of loss you want, Huber loss. That's we already created the p loss function on the top, right? You get that loss, then do loss dot backwards and optimizer dot step backwards. This is what you visualize. You can always plot these losses, like someone asked, you can plot the losses or the values to check for different time steps how it works. Okay, this is how the sampling looks like. So here the sampling is not very clear because you have to remember it's not very pixelated. It's very pixelated because the original images are all 28 comma 28. That's why the sampling looks like very bad over here. So here we're just randomly sampling some images. So yeah, this is whole the entire diffusion DDPM's work. I know there are a lot of components. It also took me time when I initially started getting into this. It definitely takes some time because there's a lot of flow of there are a lot of things that you have to keep in mind before actually getting into the code. So I hope at least some part of it you're able to get a brief idea about how the data is flowing and what are all the different blocks. Do check it out on your own time. Look at it line by line and do let me know if you have any questions in next week. Okay. For now, any questions? Anyone else? Yeah.
Yeah, so I remember that you said that sampling happens only in the reverse process.
No, sampling happens after you finish the training.
There are two algorithms. One is the training
Training algorithm, yes.
other is sampling algorithm.
Sampling algorithm, yes.
So this is kind of during inference, is it?
Yeah, no, sampling also happens during training, but inference definitely we're just doing samplings because you have to go back also, right? In reverse process also. So we do sampling also during the training time.
During training time in reverse process.
Yes, all in the reverse process. In the forward